Welcome to Business Statistics. In this video, we are going to apply the normal model in order to solve standard normal computations. So let me begin by sharing a screen to a whiteboard that will define what this means. So in the first place, what is a normal model? The normal model, which is described in Chapter 7 of your textbook, a probability model. So it measures the three aspects of uncertainty that are measurable. Okay, so in a normal model, you have a variable x, which we call random, because we are unsure as to which values it will take. So it's a variable subject to uncertainty. And as any variable subject to uncertainty, there are three things we measure. Probability, a expectation, and a deviation around the expectation. So those are the three characteristic computations of any probability model, where we assess what's happening and how often things happen to this phenomenon x, to this valuation variable x. In this case, x is additionally a continuous variable, which means that x takes on the numeric values along a spectrum of possibilities without any jumping around, without any self-assessed values that do not share neighbors or values that are contiguous. So it is a continuous variable. X is also symmetric. So because it is symmetric, we know that the mean, the median, and the mode are all equal. And in addition to that, X follows a very specific relationship between the probabilities of the model and the values of the variable. X follows the 68, 95, 99.7 rule. This particular rule tells you that 99.7% of all values are contained within 3 standard deviations of the mean, 95% within 2 deviations from the mean, and 68% within 1 deviation from the mean. I'm going to demonstrate this by using a STATCRUNCH calculator. And in STATCRUNCH, you have a calculator under Stat, and calculators. Normal. So I'm going to go open that calculator right now. I'm going to share that screen. And I'm going to go to Stat, Calculators Normal. The normal distribution is about 2/3 down the list of all calculators there. And I'm going to introduce the calculator in the between mode. So I'm going to click on the button that says between. And automatically notice how when we have what's called a standard normal is when the mean of the variable is 0 and the standard deviation is 1 unit. Notice how within 1 standard deviation of the mean, we get about 68% of the entire set of possibilities of the curve. If I change the 1 to a 2 and the -1 to a -2, then we get a description that tells us that roughly 95% of the values happen within 2 standard deviations of the mean above as well as below the mean. And if I go 3 standard deviations below to 3 standard deviations above, we end up considering almost everything possible. 99.7% of the model is contained within 3 deviations or between 3 deviations of the mean. In between mode, I could also isolate from the center to the 1 deviation mark, and that's obviously going to be roughly 1/2 of 68%, so it's 34% due to the symmetry in the model. If I go 2 deviations in 1 direction, I get about 47.7%, which is roughly half of 95%. And if I go 3 deviations to the right, then that's nearly 49.9%, half of 99.7%. So I could always look at ranges that fall within 1 standard deviation of the mean. So between 2 and 3 deviations, there's a little bit close to 2.5% of the data. Between 1 and 2 deviations of the mean, there's a very small area of about 13.5, 13.6%, and so on and so forth. Now, if I want to measure half of the area of the model, then what I see is that half of the model is about 2/3 of a deviation above average to 2/3 of a deviation below average, which means that the interquartile range of a normal model is about 4/3 of a standard deviation. So I'm going to now summarize those particulars in our whiteboard and explain what we mean by X following the 68, 99, 95, 99.7 rule. So what we mean by that is that the values of a variable are laid out along the horizontal axis. And that is true for any variable X that is normal. And we can also, in parallel, describe the variable in standard deviation units. So we're going to call that a z-score, just like we did in chapter 3. Okay. So that scale is going to be in blue. And whenever you graph a normal model in terms of its z-scores, that is what we call the standard normal. In either case, what we're looking for is a model in which a bell curve shape distribution happens, where the mean happens to be centered at the peak of the model, at the point of highest probability. So whether we're talking about a z-score, in which case we're talking about a value of 0 happening, you will see that you have 3 standard deviations from the mean. Inside of 1 deviation from the mean, you will see a range of about 68% of the model. Okay, so this area that I'm highlighting in green here is 68% of the whole model. And if I then extend this range by 1 more deviation each way, so if I go and from 1 to 2 deviations below average to 1 to 2 deviations above average, and I add those areas to the story here, then what I'm getting in pink and in green combine to 95% of the model, 95% of possible values, 95% of the time. And last but not least, if I add 1 more standard deviation to the right of the pink zone and to the left of the pink zone, I get that the combined areas form a percentage of 99.7% of all values. Okay, So that is our storyline for the normal model, where we have 3 different ranges. The 68% in the green, the 95% in the green plus the pink zone, and the 99.7% that is in the combined pink and orange and green zones together. It's the name 68, 95, 99.7 for the whole model. Okay. And a couple of more characteristics that are going to come in handy throughout the chapter are that in a normal model, the interquartile range, the range that covers the middle half of the model, which is still quartile 3 minus quartile 1, just like in its original definition in chapter 3, you will find that in a normal model, that is 4/3 of 1 standard deviation. So if the standard deviation, say, is 30, the IQR would be 4/3 times 30, or 40. The interquartile range would be a total of 40 units between the 2 values. And then in terms of metrics, the mean would occupy the central value. The mean plus 1 deviation plus 2 deviations and plus 3 deviations would occupy, respectively, the locations that you see happening here. We use the Greek letter S to denote standard deviation. And we use the letter M in the Greek alphabet to denote the mean. Middle value. And likewise, if I look at distances that are below average by 1 deviation, or by 2 deviation, or by 3 deviations, they're going to be located where the z-scores are -1, -2, and -3, respectively. So that's our preamble on the normal model. The normal model will have what's happening being described in the horizontal axis, and how often being described in probability terms on the vertical dimension. This is the what's happening dimension horizontally, and the how often dimension will be vertical. Model 1. Model 2 is, or idea number 2 in this chapter, is that this normal distribution is very, very useful. It can be applied in settings that are not normal. so long as the mean and the standard deviation that you employ are characteristics of the model that you are approximating or that you're estimating by a normal situation. So the normal model is going to be applied throughout the lab and the quiz in Chapter 7 in different contexts. One context will be in a compound or composite context where you have a model that has several parts and each part is normal, so their combination is also normal. The combination of all parts is normal. So I'm going to construct an example of that. The second example that I'll work on is an example of a binomial model that is going to be approximated by the normal model. And the third example that we're going to work on is of a Poisson model that is also estimated through a normal situation. In all situations that you apply a normal model, you have to apply a rule that you learned in Chapter 5 called the law of large numbers. The outcome of using the normal model in order to estimate probabilities of a binomial or a Poisson or a combination of many normal components is based on the idea that you have a lot of different times that normal values arise in your computations that are relevant to modeling situations in the real world. So what we're going to therefore go to now is contexts in which that happens. Before I do that, I'm going to go back to the situation here and show you why it is that a normal model is a good approximation to probabilities that may not be normal. I'm going to start with a binomial situation. So in this binomial situation, I'm going to try something out 100 times. I'm going to ask people what their favorite soft drink is. If it's Coca-Cola, we will count people in a group called the Coca-Cola group. And then the other group will be called a non-Coca-Cola group, or the rest of them. I'm going to assume that 40% of people like Coca-Cola, and that 60% of people therefore do not, because that would make up the whole story in a setting that is binary. Either you like Coca-Cola or you don't. And if you repeat this task 100 times, then you end up with a binomial situation where you can count X. X can be the number of people who like Coca-Cola in a sample of 100 people. And as such, we can calculate the expectation of X. And the expectation of X is going to be N times P, which is 40. And then we can measure the standard deviation of X, which is the square root of N times P times Q. Those formulas came from Chapter 6, where we studied the binomial model. So now the expected value and the standard deviation value are going to supplant the 0 and the 1 of the standard normal calculator. So let me go ahead and calculate the expectation and the deviation. I'm going to go Data, Compute, Multiple Expressions, because I'm going to do 2 expressions. And these 2 expressions, one is going to be called the mean, and the other one is going to be called the standard deviation, which I'm going to put in caps to not confuse the model, the STATCRUNCH, with the earlier story of little sd being this formula here. So I'm going to take this formula from the sheet called the expected formula, and I'm going to take the standard deviation formula and paste it in the SD calculation, and I'm going to let the software do the math for me and the mean and the standard deviation of the model. So as expected, in a group of 100 people with a 40% ratio of people who prefer Coca-Cola, I would see 40 people who like Coca-Cola in the sample of 100, but I wouldn't see 40 all the time. The variation is roughly 5, give or take 5 people from 40. So now I'm going to change the mean to 40 in the calculator, and I'm going to change the standard deviation to 4.898979, just to be super precise. Sorry about the comma there. I'm going to put a period because it's the decimal. And then I'm going to put here 68%, because if I am anywhere near right, what I should see is that the two answers here should be roughly 35 to 45 people. Roughly 35 to 45, because that's about one deviation from the mean, and that's how far 68% of the data would lie per the normal situation. Now what I'm going to do is open a calculator, stat calculators, binomial. I'm going to open the exact calculator, and where n equals 10 right now, I'm going to set that to 100, and where p equals 0.5, I'm going to set that to 0.4. And then I'm going to set this to the between model, and I'm going to set the bottom number to 35 and the top number to 45. And I should also see roughly 68%. It's not roughly 68%, so I'm going to go 44 to 36. And that's a little below 68%, so 44.5 to 36.5 will give me, sorry, to 34.5 will give me roughly 68% of the curve in the red bars. So notice how very similar, notice how the curve on the left approximates, notice how the normal model approximates the binomial story on the right. Normal on the left approximates the binomial on the right. And I hope that this image captures the so-called normal approximation to a binomial calculation. Binomial probability calculation. Okay, and expected value is right at 40, and the standard deviation is in effect n times p times q square rooted, which is 4.9 roughly. So notice how, in order to get the closest, most accurate value, instead of using the numbers 35.12 and 44.87, I approximate counts here by a half a unit, by give or take a half a unit, in order to measure more accurately. So an interesting part of using the normal model to approximate a binomial you should round up or down by 1/2 a unit from the whole value. That will ensure more accurate estimates of a normal probability model. So that's the only caveat in normal approximations. Now let's move on to looking at another model, a Poisson model. So if I go stat calculators Poisson, and in the Poisson I use a mean of 40. Notice how the Poisson model looks very similar to the binomial calculator, and it also looks very similar to the normal calculator in that range. Now, if I approximate things by 1/2 a unit again, I get an estimate, though not as good necessarily. Okay, so that's because the Poisson structure is a little different than the binomial structure, in that the mean of a Poisson and the standard deviation of a Poisson are only different by a square root of the function. So if I look at 68% of a Poisson model, I should be going 33.5 to 46.5. And again, we get our estimated approximation. So another note is that to approximate a Poisson model, the normal model, you should remember to use the roundup rule, but you should also remember that the standard deviation equals the square root of the mean in a Poisson. Okay, as opposed to in the binomial, which is the square root of n times p times q. Okay, so this one slide shows the importance of making the right tweaks to the normal model that you're going to use as an approximation to the binomial or to the Poisson model. I believe that in your lab and your quiz, you have a few problems where you approximate binomials, and I think you may have one that approximates a Poisson. Okay. So let's go ahead now that we have looked at this StatCrunch activity. Let's go back to sharing the whiteboard. And we're going to do 3 problems in this video. So problem 1 is a binomial probability that is approximated with a normal model. Okay. And in one of your lab questions, you develop a country develops a new coin. The design claims that the coin is fair, which means that it's a 50% heads, 50% tails coin. And it never lands on the edge. And you test the coin by flipping it 300 times, which should be a lot of repetitions, very important. So the law of large numbers kicks in. And you see it land heads on 170 occasions. On 170 of the tosses. So what that means is that it lands tails 130 times. Okay, so you're supposed to see it land 150 times heads and 150 times tails, but you don't. You see it land 170 times heads and 130 times tails. So the question I have is, what is the probability that this coin may still be considered fair, even though it landed heads more often than tails. Okay. So step one is set up the binomial story or the binomial model. Based on the theoreticals. So in this case, N is 300, P is supposed to be 50%, and Q is supposed to be 50%. So if you then put this information into STATCRUNCH, then the mean will be N times P, which is 150. It's 300 times a half. And then the standard deviation should be the square root of N times P times Q. And that should be equal to the square root of 75. Which we should know is about 8.6 or so. So when we calculate the square root of 75, I'm going to do that in a normal, in a cell phone calculator. At 8.66. Okay, so that's the mean and the standard deviation. And now we're going to approximate the binomial with a normal model that has the same mean and the same standard deviation. Okay. So what I'm going to do is open StatCrunch, open the calculators, go to the normal calculator. The dialog window will set open, and I'm going to set the mean equal to 75, set the standard deviation equal to 8.66, and then set the probability statement to x being greater than or equals to 169.5 to make the half a unit adjustment from 170. Okay, so I want you to recognize that this 170 here is written as to include the whole of 170. I back off by half a unit there, and that's going to be my answer. So let me go into StatCrunch and set the values here to 300, 0.5, 0.5. Run the two calculations. The two calculations are 150 and 8.66. And I'm going to go to the standard calculator and look beyond 169.5, which is how I approximate 170. And I get that the chance that this coin is a fair coin when you see it land heads 170 or more times is only 1.22%. Okay, so I'm going to go back to my story in the whiteboard, and the answer is 0.0122, rounded to 4 decimals. So there's almost no way that this coin could be fair, so to speak. So that would be the assessment. There's only a 1% chance that this coin is a 50% heads tails coin when you see it land 170 times on heads and 130 times on tails. And that is how you perform a normal approximation of a binomial. Okay, so again, first, get the binomial characteristics from the problem reading. Second, calculate the mean and the standard deviation. Third, convert the mean and the standard deviation in the normal calculator to those values. And fourth, apply the correct probability computation, be it standard or between, in the process. And that is how you calculate a binomial probability using the normal model. The next problem is going to be a problem where we use the normal model to combine several normal components into one normal. Compound. And these problems are very useful in a field called logistics, where there are several uncertainties that are intricately sequentially tied to one another. Okay, so in one of your quiz or lab questions, there's a problem about a situation where you have a bicycle assembly problem, and the first part of the problem is about being able to pull the correct bicycle for the client that the client wants. The second is mount all the components together, assembly. And the third is the fine-tuning of the bicycle in order to deliver it to the customer. And then you combine the three parts. Another problem in this situation is a cereal problem, where you have a box of cereal and you pour a big bowl out and this little bowl out, and you are doing a calculation on what should remain in the box after you pour the two bowls out. So all these problems of this nature have sequences of parts, and these sequences follow one another. There's another problem where you have 4 swimmers doing a relay swim race, and in the relay they each have a mean and a standard deviation. Okay, so what's typical about these models is that they have a part and each part has its own mean and its own standard deviation. And so the first thing to do is to combine all these ingredients into a single model, and that model is called a compound model. And the mean of the compound model is just either the sum or the difference or the subtraction of the parts. So you just take each mean and you add each mean to the other mean, and the compound will have, that's how you calculate the mean for the compound. And the compound for the standard deviation will be the square root of the standard deviation of each part squared. So you first convert each standard deviation to a variance. And after you have the variances of the components, you add them all together. And after you add them all together, you square root that total variation in order to capture the standard deviation of the compound. And one caveat is you have to make an assumption. You must assume that the three parts are independent of each other. Otherwise, there are correlation factors between the three parts that have to be accounted for. And once you have the compound mean and the compound standard deviation, you then proceed to do exactly what we did in the binomial story of the earlier story, which is you go, step one is you open StatCrunch. So you go to Stat, Calculators, Normal. And when it opens the normal calculator, you set the mean and standard deviation to the compound computations. And after you do that, you then set the question as if it were one normal problem. So that's essentially how you operate on the many different questions that use this approach in this format. So one of the problems was the swim relay race, where each athlete had a different part of the race. So it's just the first variable plus the second variable plus the third variable plus the fourth variable. There was another problem where you did the bike assembly. That one had three parts only. So you take the inventory search of the bike to the assembly of the components to the fine tuning. The cereal box problem. In the cereal box problem, you take the cereal box and you subtract the large bowl, pour out, and you also subtract the small bowl, pour out. So if you're not getting the right results in that problem, make sure you don't add, make sure you subtract what you're taking out of the box to know what's left over in the box. And that's going to be called the leftover in new box. The bike assembly problem is called time to delivery of bicycle to a customer. And the swim relay race is the time to complete the 4 stages of the bike. So the first 2 were additions, and the third one was a trickier one because it involved subtraction. So I'm going to let you try these problems and contact me if you have any questions about how to complete them over the next few days. Then in a Poisson problem, even though you don't have one in the lab in the quiz, I'm just going to work on one. I'm going to suppose that crime in a large, densely populated city is a problem, and in particular, the number of violent crimes follows a Poisson model in which 225 violent crimes occur per month in the city. So what do we know from that particular model? What we know from that model is that the mean of the Poisson is 225 crimes per month, violent crimes per month. And that the standard deviation is the square root of 225, which is 15 violent crimes per month. Going back to the third part of the problem, the city has implemented a new community policing strategy to alleviate citizenry's suffering from violent crime. Six months into the program, we observe 170 violent crimes. See, it's 180 violent crimes. So the question then becomes, is the policing strategy, is the community policing strategy working? And to answer the question, calculate the probability that 180 or fewer violent crimes are observed in this city. So again, remember the mean is 225, and the standard deviation is the square root of that, or 15. So remember those two parameters of this model. And we're going to plug that into a normal story. Okay, so I'm going to draw the normal story here. That's an approximation, of course. But I do know that in this approximation, the center here is 225. And every 15 units, I'm going to put in a standard deviation. So notice how I built a scale that has 3 deviations right and left. Notice that the axis that I've built is centered there. And notice that my graph is just a little messed up. It's a little skewed to the right. So I'm going to warp it a little bit. And the middle is still at 225. So if I look at the number that I'm interested in counting the odds of seeing, which is 180 or fewer, 180 is actually really far from the expected or usual number of 225. In effect, in this context, the 180 has a z-score that is -3. It's 3 deviations below average. So even without doing the math, I can already tell that this probability is going to be super small. It's going to be in the neighborhood of 0, 0, 3, 0, 0, 1, 5, 0, 0, 2, 0, 0, 1, 5, or so. That's from the 99.7% of the values that are occupying the interior of 3 deviations here, which is 99.7%. And that means that the leftover is 0.3%, and half of that would be on the above 270 crimes, and half is below 180. And so I'm estimating that my probability for this answer is super low. It's nearly impossible. It's 1 to 2 in 1,000. The chance that crime has gone down 100 to 180 events per month just randomly. It's nearly impossible for that to happen just randomly. So, since the probability of observing 180 or fewer crimes in a month for a city that usually experiences 225 crimes, give or take 15, is 0.001 something, 0.0015 approximately. And the implication of that is that it's nearly impossible for that to happen randomly. So since the probability of observing 180 or fewer crimes in a month for a city that usually experiences that is 0.0015, we can conclude that something not non-random is behind the decline in crime. And by something non-random, which the only thing that we did differently in terms of action against violent crime is community policing. So community policing may be effective in the city. And so how did I get this 0.0015? Well, you go to STATCRUNCH, you put in the mean, in the binomial and the standard deviation, and then you calculate the probability of seeing fewer than 180 crimes, or sorry, more, fewer than 180 crimes, and the answer is 0.0012. And so 0.0012 is a very small probability. You can't even see the little red tinge on the left of the bell curve because it's so small. But that 0.0012 is the precise calculation using STATCRUNCH. Okay. If I do not do the half a unit approximation, it's 0.0013, which is very close to my 0.0015 that I initially estimated. So But the point is that the chance of seeing so little crime in a city that sees an average of 225 plus or minus 15, that's nearly impossible from a random or in a random system, or randomly speaking. And since nearly impossible randomly, then there must be something non-random behind it, and that would be the community policing having a significant impact. So when you hear sentences like, this program has a statistically significant impact on the number of events you observe, that's what this means. It means that you found a low chance that the impact that you're measuring is random. And since it's a low probability for randomness, it's a high probability for non-randomness. And that's how you would apply the situation to a Poisson problem that you wanted to approximate via the normal model. Thank you for watching this video, and I hope it was useful in that it enables you to complete Chapter 7 lab and Chapter 7 quiz, and also exam 3. Bye-bye.